Imagine floating around in space, amongst the stars, experiencing zero gravity, going somewhere where very few have been before. It's almost like you're flying. It's almost magical.
Unfortunately, for most of us, we'll never get to experience this. My name is Marcus Eymael, and in collaboration with Dr. Nam Tran and Miss Fiona Deutsch, for the past year we've been working on the design of a low-cost random positioning machine, or RPM. Now, you may be asking yourself, what does this have to do with space? Well, that's a very good question. An RPM is used to simulate microgravity. It consists of two independently driven axes that are perpendicular to each other. Microgravity is simulated by random motion in both axes. This averages the gravitational loading after some time to zero, mimicking the gravitational loading on board a spacecraft, the Moon, or even Mars. These were first developed not only due to the exorbitant costs associated with sending specimens into space, but just the lack of regular testing. So, why don't you join me on this journey and let's have a look at what went into designing this low-cost RPM. So, what's the problem? Well, when you look at the RPM market, it becomes apparent very quickly that there are two main issues that need to be addressed. One of those being the price. With current commercially available options, such as the one by Airbus Space and Defence, costing in excess of $10,000, and this doesn't even include the ongoing maintenance costs. This therefore prevents smaller research labs or even institutions such as UTS from purchasing this technology due to the prohibitive financial barrier. Furthermore, the platforms which hold the specimens have yet to be optimised for scientific equipment. As you can see in the photo, they're utilising a bit of Velcro strap to hold it down. All in all, this research is critical as it allows us to understand the physiological degradation that cell cultures go through when experiencing microgravity. This is something that we're yet to fully explore. Throughout Capstone, there are a multitude of challenges that I face. The three main challenges were the need to switch printers, as initially I was utilising my own personal printer, with PLA as the material of choice. However, I soon found out that the parts weren't going to fit, and in fact, PLA was not an optimal choice due to the low glass transition temperature. Ultimately, I went to the UTS protospace and utilised the Stratus 450MC, with ASA as the material of choice due to its higher glass transition temperature. My next challenge was the lack of resources on optimal spin rates. In order to overcome this, we utilised an accelerometer in order to determine our own spin rates through testing. Finally, was how we were going to transfer power and signal into a rotating frame. After some Googling, I soon found out that there was an electromechanical device known as a slip ring commutator that would allow me to do this. Something that I'd been dreading throughout my entire capstone was how we were going to achieve random motion in both axes. From literature I'd reviewed, random motion was required in order to achieve microgravity. As you can see here in figure 1, when you have both axes spinning at an equal rate, microgravity is not achieved, whereas in figure 2, when you have random motion, microgravity is achieved. The big breakthrough was when I was collaborating with Mr. Paleo on the coding of the algorithm. As we were using a timer to determine the length of the experiments, we could have a couple lines of code that when it encountered a multiple of a certain number, would change spin direction. So, with a couple lines of code, we were now able to simulate microgravity.
Motion for the RPM device is provided by two stepper motors, a NEMA 14 and a NEMA 23. These are controlled by two stepper motor digital drivers and an Arduino. These are able to regulate spin rate and direction. The frame is 3D printed out of acrylonitrile styrene acrylate, or ASA. It is held together with machine screws. On the left-hand side, you'll also be able to see the slip ring commutator which we previously discussed. This allows the transmission of power and signal into the rotating frame. An Arduino Nano is also built into the frame and is being used to monitor acceleration and temperature, which is critical for experiments. All up, this has resulted in a setup that costs just under $1,000. This low-cost RPM has the same functionality as the commercially available options, however, just for a tenth of the price.
Although the idea behind RPM devices isn't anything new, there are a couple factors that set this device apart from currently available options. First off, it is the most affordable RPM on the market, coming in at less than $1,000. This is a tenth of the price of one of the most popular RPMs, the RPM 2.0 from Airbus Space and Defence, which you saw earlier. It is also the first RPM to utilise 3D printing for the majority of its construction, with most RPMs using machine parts, which is a large contributor to the higher cost. As you would have previously seen, the specimen holder is modular, and since it's been designed to fit the largest culture flask that is often utilised in cell culture research, we are able to print up other holders for the smaller T25 flask or even a Petri dish. Now, whilst we've targeted mammalian cell culture research, there are so many other research fields that microgravity is applicable to. A quick search on Google and you'll find papers looking at head and neck cancer research or even better treatments for osteoporosis. So, by providing this affordable option, we are making innovation more accessible to the wider scientific community. So, as you can see, there is huge commercialization potential for this RPM device. All the components are off the shelf and are easily sourced from suppliers such as Element 14 or RS Components. The design itself is also easily transferable to injection molding for potential mass production. It is also a relatively simple design, requiring only one Allen key and a set of hands to build due to the standardization of fasteners throughout the build. The algorithm that is used to control the motors is also upgradable, so users can customize it as they see fit for their use case. Ultimately, the low cost removes the financial barrier that has held back research from being conducted, and as previously stated, it would bring back innovation into the wider scientific community that has been lacking for so long. Moving forward, there are a couple more key things that need to be addressed before full commercialization. Refinement on the design is required in order to make it more appropriate and robust for lab use. Also, just to give it a more polished and professional look, because as it currently stands, it is just a proof of concept. An IKEA-like set of assembly instructions along with production-ready drawings are to be developed. On the cards right now is the development of a mobile app that is able to remotely control and monitor the experiments from the comfort of your own home. Finally, for the production of these RPMs, a partnership with a manufacturing lab such as the Protospace is a potential option to be considered. During discussion, the idea of making the design open source has been raised. The idea is to follow a similar model to that of OpenPCR, which is an open source design where kits can be purchased by users who don't have the resources to manufacture the parts. As the design is open source, improvements have been made due to the collaboration that has occurred in the community, ultimately bettering the product. Whilst this may not be as lucrative as selling the product outright, it would even further increase the accessibility of RPM technology and could potentially lead to some really exciting developments as already seen with OpenPCR.
Thank you for watching. I hope you now understand the role RPMs play in the study of microgravity.